What is RF module and how does it function? An RF module, radio frequency module, is a small electronic device used to transmit and receive radio signals between two devices. It operates within a specific frequency range, typically from megahertz to gigahertz, and is widely used in wireless communication systems. RF modules play a critical role in applications such as remote controls, wireless networks, IoT devices, and more. RF modules can be categorized based on their functionality, communication frequency, and protocol. Below is an overview of the common types. 1. Based on functionality. Transmitter modules, TX, designed only to send data via RF signals. Used in devices like remote controls or wireless sensors. Example, 433 MHz RF transmitter. Receiver modules, RX, only receive data sent via RF signals. Used in applications like wireless receivers for remote controls. Example, 433 MHz RF receiver. Transceiver modules, capable of both transmitting and receiving data. Widely used in applications like Bluetooth, Wi-Fi, and Zigbee. Example, NRF24L01, 2.4 GHz transceiver. 2. Based on frequency. Low-frequency RF modules operate in ranges like 315 MHz or 433 MHz. Applications, remote controls, simple data transmission over short ranges. Example, ASC, amplitude shift keying, based RF modules. High-frequency RF modules operate in gigahertz ranges like 2.4 GHz or 5 GHz. Applications, Wi-Fi, Bluetooth, Zigbee, cellular communication. Example, Wi-Fi modules, e.g., ESP8266. Ultra-low power modules operate at sub-GHz frequencies, e.g., 868 MHz or 915 MHz. Applications, long-range IoT systems like LoRa and Sigfox. Example, LoRa SX1278 module. 3. Based on communication protocol. Wi-Fi modules operate on 2.4 GHz and 5 GHz bands using the IEEE 802.11 standard. Applications, wireless LANs, IoT devices. Example, ESP32, ESP8266. Bluetooth modules operate on 2.4 GHz using the Bluetooth protocol. Applications, short-range communication, e.g., headphones, smartwatches. Example, HC05, HC06. Zigbee modules operate on 2.4 GHz and follow the IEEE 802.15.4 standard. Applications, low power, mesh-networked IoT devices. Example, XB module. LoRa modules operate at sub-GHz frequencies, e.g., 433 MHz, 868 MHz. Use long-range and low-power communication. Applications, IoT networks, remote sensing. Example, LoRa SX1276/1278. GSM/GPRS modules operate on cellular networks. Applications, SMS-based systems, GPS tracking. Example, SIM800, SIM900. RFID modules operate at various frequencies like 125 kHz or 13.56 MHz. Applications, access control, inventory management. Example, MFRC522. 4. Based on application. Simple data transfer RF modules operate on 315 MHz or 433 MHz using basic ASC/FSK modulation. Applications, remote controls, simple wireless systems. Example, XY-MK5V. High bandwidth RF modules operate on higher frequencies like 2.4 GHz or 5 GHz. Applications, video streaming, high-speed data transfer. Example, Wi-Fi 6 modules. IoT-specific RF modules operate on various frequencies optimized for IoT protocols. Example, NB-IoT, Zigbee, LoRa modules. RF, radio frequency. Modules work by enabling wireless communication between devices through the transmission and reception of radio waves. Here's a breakdown of how they function. 1. Transmission. Input signal. The system begins with an input signal, usually in digital form, e.g., data from a sensor or microcontroller. Modulation. The input signal is combined with a high-frequency carrier signal using modulation techniques, e.g., AM, FM, or digital techniques like FSK, PSK. Modulation ensures the data can travel over long distances without degradation and aligns with the required communication frequency. Amplification. The modulated signal is amplified to increase its power and ensure it can travel the intended distance. Emission. The amplified signal is transmitted into the air via an antenna. 2. Propagation. The transmitted RF signal propagates through the air as electromagnetic waves. Environmental factors like obstacles, interference, and atmospheric conditions can affect signal strength and clarity. 3. Reception. Antenna reception. The receiving antenna captures the transmitted RF waves. Signal demodulation. The received RF signal is demodulated to extract the original data embedded in the carrier wave. Signal filtering. Filters are applied to remove noise and unwanted frequencies, ensuring only the desired signal is processed. Amplification. The weak received signal is amplified to make it suitable for further processing. 4. Data output. The extracted signal is converted back into its original form, e.g., digital or analog data. This output can be fed into a microcontroller, computer, or other devices for interpretation or use. Key concepts in RF module operation. Modulation. The process of encoding data onto a carrier frequency. Common methods include AM, amplitude modulation, varies the amplitude of the carrier wave. FM, frequency modulation, varies the frequency of the carrier wave. Digital methods, FSK, frequency shift keying, PSK, phase shift keying, QAM, quadrature amplitude modulation. Frequency bands. RF modules operate within specific frequency bands, such as 315 MHz, 433 MHz, 868 MHz, 2.4 GHz, or 5 GHz. The choice of frequency affects range, data rate, and interference susceptibility. Power levels. RF power determines the range and strength of the transmission. Low-power modules are used for short-range communication, e.g., Bluetooth, while higher power modules are for long distances, e.g., LoRa. Antennas. Essential for both transmission and reception. The design and placement of antennas significantly influence signal quality and range. Example, working of a 433 MHz RF module. Transmission. A microcontroller sends digital data to the RF transmitter module. The transmitter modulates this data onto a 433 MHz carrier wave and emits it via its antenna. Propagation. The RF signal travels through the air. Reception. The receiver module's antenna captures the RF signal. The module demodulates the signal to retrieve the original digital data. Output. The received data is sent to another microcontroller or system for further processing. Advantages of RF modules. Wireless communication. Eliminates the need for cables. Wide range. Can operate over distances ranging from a few meters to several kilometers. Low power consumption. Ideal for battery-powered devices. An RF, radio frequency, module consists of several key components that enable it to perform wireless communication. Each component plays a crucial role in the transmission, reception, modulation, and amplification of RF signals. Here's a detailed look at these components. 1. Oscillator. Function. Generates a stable carrier frequency, e.g., 433 MHz, 2.4 GHz, for transmission. Type. Typically a crystal oscillator or a phase-locked loop, PLL. Importance. The accuracy and stability of the oscillator determine the reliability of communication. 2. Modulator/demodulator. Modulator. Combines the baseband signal, data, with the carrier frequency. Implements modulation schemes like amplitude modulation, AM, frequency modulation, FM, digital modulation, e.g., FSK, PSK, QAM, converts the input signal into a format suitable for transmission. Demodulator extracts the original data from the modulated RF signal received, performs the reverse process of the modulator. 3. Amplifier function boosts the strength of the signal for transmission. Transmitter amplifier enhances weak signals received by the antenna. Receiver amplifier types: power amplifier, PA for outgoing signals; low noise amplifier, LNA, for incoming signals to reduce noise. 4. Antenna function converts electrical signals into electromagnetic waves for transmission, captures electromagnetic waves, and converts them back into electrical signals for reception. Design depends on frequency, application, and desired range. Types include dipole, monopole, patch, loop antennas. 5. Filters function remove unwanted signals and noise from the transmitted and received RF signals. Types: bandpass filters allow only specific frequency ranges. Low-pass filters allow frequencies below a certain threshold. High-pass filters allow frequencies above a certain threshold. 6. Mixer function combines or shifts the frequencies of the incoming or outgoing signals. Use in receivers, it converts RF signals to intermediate frequencies, if for easier processing. In transmitters, it upconverts baseband signals to RF frequencies. 7. Microcontroller or baseband processor function provides logic control for the RF module, encodes and decodes the data before modulation and after demodulation. Example: in modules like ESP8266, a microcontroller handles both RF communication and user applications. 8. Matching network function matches the impedance of the antenna with the RF module's transmitter or receiver circuits. Importance: maximizes power transfer and minimizes signal loss. 9. Transmission line function connects the RF circuitry to the antenna. Types: coaxial cables, microstrip lines. 10. Power supply unit function provides the required voltage and current for the RF module's operation. Consideration: low power consumption is critical for battery-operated devices. 11. Memory optional function stores configurations or settings for the RF module, used in advanced modules for storing firmware or protocols. 12. Communication interfaces function allows the RF module to communicate with a host device, e.g., microcontroller or computer. Types: UART, SPI, I2C. Key example components in specific RF modules: NRF24L01, 2.4 GHz transceiver module, oscillator, crystal, modulation, GFSK, Gaussian frequency shift keying, interface, SPI, antenna, PCB or external, ESP8266, Wi-Fi module, oscillator, integrated, modulation, OFDM, orthogonal frequency division multiplexing, processor, integrated microcontroller, interface, UART, SPI, RF, radio frequency. Modules are versatile components used in a wide range of applications due to their ability to enable wireless communication. Below are some of their common uses. 1. Remote control systems. Application areas: home automation, remote controls for garage doors, lighting systems, fans, and appliances. Toys, remote-controlled cars, drones, and airplanes. Industrial automation, remote operation of machinery and equipment. Example modules: 433 MHz RF transmitter and receiver modules. 2. Wireless communication. Application areas: Wi-Fi networks, for internet connectivity in homes, offices, and public spaces. Bluetooth devices, short-range communication for peripherals like headphones, keyboards, and smartwatches. Walkie-talkies, for direct point-to-point communication. Example modules: ESP8266, Wi-Fi, HC05, Bluetooth. 3. IoT, Internet of Things, applications. Application areas: smart homes, connecting sensors, cameras, and appliances to a central hub or app. Smart cities, traffic monitoring, waste management, and public safety systems. Wearable devices, fitness trackers, and smartwatches. Industrial IoT, monitoring and controlling factory operations remotely. Example modules: LoRa SX1278, long-range IoT, Zigbee XB. 4. Wireless sensor networks. Application areas: environmental monitoring, temperature, humidity, and air quality sensors. Agriculture, soil moisture sensors and irrigation systems. Health monitoring, wireless patient monitoring systems in hospitals. Example modules: NRF24L01, Zigbee. 5. Telemetry and remote monitoring. Application areas: vehicles, monitoring tire pressure, engine diagnostics, or GPS tracking. Utilities, smart metering for electricity, gas, and water. Aerospace, telemetry systems in satellites and rockets. Example modules: GSM/GPRS modules like SIM800, LoRa modules. 6. RFID applications. Application areas: access control, key cards for secured areas and buildings. Inventory management, tracking goods in warehouses. Retail, contactless payment and product tracking. Healthcare, patient and equipment tracking in hospitals. Example modules: RFID reader modules like MFRC522. 7. Consumer electronics. Application areas: TV remotes, RF-based remotes for TVs and set-top boxes. Gaming consoles, wireless controllers for a seamless gaming experience. Home audio systems, wireless connectivity between devices. Example modules: Zigbee or Bluetooth modules. 8. GPS and navigation systems. Application areas: vehicles, real-time location tracking and route planning. Outdoor sports, wearable devices for tracking hiking or cycling routes. Asset tracking, monitoring the movement of goods or equipment. Example modules: GPS modules like Neo 6M combined with GSM/GPRS for data transmission. 9. Security and surveillance. Application areas: CCTV systems, wireless cameras for homes and businesses. Intruder alarms, RF-based motion detectors, and door/window sensors. Baby monitors, wireless audio and video monitoring. Example modules: Wi-Fi modules, Zigbee modules. 10. Robotics. Application areas: remote-controlled robots, using RF modules for communication. Swarm robotics, coordinating multiple robots via wireless communication. Drones, control and telemetry in unmanned aerial vehicles. Example modules: 433 MHz RF modules, NRF24L01. 11. Automotive applications. Application areas: keyless entry systems, using RF signals to lock/unlock car doors. Tire pressure monitoring, wireless sensors in each tire. Engine diagnostics, remote transmission of engine health data. Example modules: sub-GHz RF modules, LoRa. 12. Military and aerospace. Application areas: communication systems, secure, long-range communication for field units. Radar systems, RF waves for detecting objects and their motion. Satellite communication, transmitting data to and from satellites. Example modules: custom-designed RF modules for specific applications. 13. Healthcare applications. Application areas: medical devices, pacemakers and glucose monitors with wireless capabilities. Patient monitoring, tracking vital signs remotely in real time. Telemedicine, wireless communication for diagnostics and consultations. Example modules: Bluetooth LE modules like HM10. 14. Entertainment and multimedia. Application areas: wireless microphones for performances, conferences, and events. Streaming devices, Wi-Fi-based RF modules for audio and video streaming. Smart TVs, remote connectivity and control. Example modules: Wi-Fi or proprietary RF modules. RF, radio frequency, modules offer several advantages that make them a popular choice for wireless communication in various applications. Below are the key benefits. 1. Wireless communication. Advantage: eliminates the need for physical connections, e.g., wires or cables. Impact: simplifies system design and installation, especially in areas where wiring is impractical or costly. 2. Long-range communication. Advantage: RF signals can travel long distances, depending on the frequency and power. Examples: low-frequency RF modules, e.g., 433 MHz, for long-range communication. LoRa modules for several kilometers in rural or open areas. 3. Low power consumption. Advantage: many RF modules are designed to operate with minimal power, making them suitable for battery-operated devices. Impact: ideal for IoT applications and remote sensors where power efficiency is critical. 4. High penetration ability. Advantage: RF signals can pass through walls, obstacles, and other materials better than higher frequency alternatives, e.g., infrared or visible light. Impact: reliable operation in indoor and urban environments. 5. Versatility. Advantage: RF modules can operate in various frequency bands, e.g., 315 MHz, 433 MHz, 2.4 GHz, and support multiple communication protocols, e.g., Bluetooth, Zigbee, Wi-Fi. Impact: they cater to diverse applications, from short-range IoT networks to long-range telemetry. 6. Scalability. Advantage: many RF communication systems support multiple devices in a network. Impact: enables complex networks like Zigbee mesh systems or LoRaWAN, which can handle thousands of nodes. 7. Cost-effectiveness. Advantage: low-cost RF modules, e.g., 433 MHz transmitter/receiver modules, are readily available for basic wireless communication needs. Impact: reduces the cost of developing wireless systems, especially for hobbyists and low-budget projects. 8. Reliability. Advantage: advanced error checking and correction algorithms ensure robust data transmission, even in noisy environments. Examples: modules with digital modulation, e.g., FSK, GFSK, provide higher reliability than analog methods. 9. Wide availability. Advantage: RF modules are widely available for different use cases and frequency bands. Impact: developers have access to a broad range of options tailored to their project requirements. 10. Compatibility. Advantage: many RF modules are designed to integrate easily with microcontrollers, sensors, and other devices. Impact: simplifies the development of wireless communication systems. 11. Flexibility in frequency selection. Advantage: RF modules operate in licensed, e.g., GSM, and unlicensed, e.g., ISM bands like 433 MHz or 2.4 GHz frequency ranges. Impact: offers flexibility in designing systems to meet specific regulatory and application needs. 12. Support for high-speed communication. Advantage: high-frequency RF modules, e.g., Wi-Fi modules, support fast data rates. Impact: enables applications like video streaming, online gaming, and real-time communication. 13. Robustness against environmental conditions. Advantage: RF signals are less affected by environmental conditions like fog, rain, or sunlight compared to optical communication, e.g., infrared. Impact: ensures consistent performance in outdoor applications. 14. Secure communication. Advantage: many RF modules support encryption protocols for secure data transmission. Examples: Wi-Fi and Bluetooth modules with WPA2 or AES encryption. 15. Support for diverse applications. Advantage: RF modules cater to a wide range of applications, from consumer electronics to industrial automation and IoT networks. Examples: simple remote controls, complex multi-node IoT systems. 16. Integration with IoT ecosystems. Advantage: RF modules like Zigbee, LoRa, and Wi-Fi are integral to IoT ecosystems. Impact: facilitates seamless connectivity between smart devices in homes, industries, and cities. While RF, radio frequency. Modules are widely used and offer many advantages. They also present several challenges. These challenges can arise due to technical, environmental, or regulatory factors. Here's an overview of the key issues. 1. Interference. Challenge. RF signals are susceptible to interference from other wireless devices operating in the same frequency band, e.g., Wi-Fi, Bluetooth, or neighboring RF systems. Impact. Reduced signal quality, increased packet loss, and lower data rates. Solution. Use frequency hopping spread spectrum, FHSS, or direct sequence spread spectrum, DSSS, techniques. Choose less congested frequency bands. 2. Limited range. Challenge. The communication range of RF modules depends on the frequency, power, and environmental factors. High-frequency modules, e.g., 2.4 GHz, have shorter ranges compared to low-frequency ones, e.g., 433 MHz. Impact. May require repeaters or more powerful modules for larger coverage. Solution. Use low-frequency modules for long-range communication. Implement mesh networks, e.g., Zigbee or LoRaWAN. 3. Power consumption. Challenge. RF modules can consume significant power during transmission and reception, especially in high-speed or long-range applications. Impact. Shorter battery life for portable or IoT devices. Solution. Opt for low-power RF modules, e.g., Bluetooth Low Energy, Zigbee. Use sleep modes and duty cycling techniques. 4. Environmental factors. Challenge. RF signals are affected by obstacles, e.g., walls, trees, weather, e.g., rain, fog, and terrain. Impact. Reduced range, signal attenuation, and inconsistent communication. Solution. Use higher power amplifiers. Deploy multiple nodes or repeaters to ensure coverage. 5. Noise sensitivity. Challenge. RF modules are sensitive to electromagnetic noise from other devices, such as motors, power lines, and electronic circuits. Impact. Increased error rates and degraded performance. Solution. Shield RF circuits and antennas. Use low-noise amplifiers and filters. 6. Security concerns. Challenge. RF communication is inherently vulnerable to eavesdropping, jamming, and spoofing. Impact. Unauthorized access or disruption of communication. Solution. Implement encryption protocols, e.g., AES, WPA2. Use secure frequency hopping techniques. 7. Regulatory constraints. Challenge. RF modules must comply with frequency, power, and usage regulations specific to each country. Impact. Limited operational freedom and added certification costs. Solution. Design modules that comply with international standards, e.g., FCC, CE. Choose license-free ISM bands for most applications. 8. Antenna design issues. Challenge. The performance of an RF module heavily depends on the antenna design and placement. Impact. Poorly designed or positioned antennas can reduce signal quality and range. Solution. Use well-matched and optimized antennas. Conduct antenna tuning and placement analysis. 9. Complex design and integration. Challenge. Integrating RF modules into a system requires expertise in RF design, impedance matching, and PCB layout. Impact. Increased development time and cost. Solution. Use pre-certified RF modules to simplify integration. Consult RF specialists or use simulation tools. 10. Cost. Challenge. Advanced RF modules with high performance or specialized capabilities can be expensive. Impact. May increase the cost of the overall system. Solution. Choose cost-effective modules that meet the application's specific requirements. 11. Data throughput limitations. Challenge. Low-frequency RF modules often have lower data rates compared to higher-frequency counterparts. Impact. Unsuitable for high-bandwidth applications like video streaming. Solution. Use high-frequency modules, e.g., Wi-Fi or 5G, for bandwidth-intensive applications. 12. Temperature sensitivity. Challenge. RF performance can degrade under extreme temperatures. Impact. Reduced reliability in harsh environments. Solution. Use temperature-compensated components and designs. 13. Latency. Challenge. RF modules may introduce latency, especially in multi-hop or mesh networks. Impact. Delay-sensitive applications, e.g., real-time controls, may face performance issues. Solution. Optimize network protocols and routing mechanisms. 14. Compatibility issues. Challenge. Different RF modules may not be compatible due to varying protocols or frequency bands. Impact. Limited interoperability in multi-vendor systems. Solution. Standardized protocols, e.g., Zigbee, Wi-Fi. Use universal communication standards. 15. Scalability challenges. Challenge. Managing a large number of RF devices in a network can lead to congestion and performance degradation. Impact. Reduced reliability in large-scale deployments. Solution. Use adaptive frequency and power management techniques. Design systems with hierarchical or mesh architectures.